Okay, so this is the third presentation for Chapter 12, the rates and mechanisms of chemical reactions. We had ended off where we were talking about the form of the Arrhenius equation, and now we're going to build more into using the Arrhenius equation, continuing on from where we were at the end of Part 2. So if we take the equation that we were looking at before and apply a little calculus to it, we get this log version here. Now this is what's actually going to be more important when it comes to plugging in values. The version we were looking at before with the steric factor and other things in Part 2, that's more of a explanation of why we're doing what we're doing. That version of the equation helps us to understand the model, but this is now the form that we'll use if we need to actually do any mathematical operations. The usefulness of this equation, just so you understand, is to get the E of A value, which can be difficult to measure for a lot of systems. So they developed this into something that you can do graphically, and later on we'll see another version where they take a difference between 2 points, and the goal of it is to get an estimated E of A, typically. Typically that's the value. Okay, so A is some factor, I don't know what it is. It's dependent on the reaction, but it's also dependent because it's kinetic. It's dependent on how the reaction is done and what all's around it. When we get to catalysis close to the end of this, we'll talk a little more about that. So A is just a thing that's very difficult to measure as well, but it'll be in common across all my different experimental parameters because I'll do the same reaction again and again with different, with different concentrations, with different setups, and that at different temperatures. So I'll be able to get a good measurement. That's the idea. So we can arrange this into a plot where we can have 1 over temperature. This is a constant m, E of A over R here, and then this is our Y value. This should not, this is K for a reaction system, so this shouldn't change if T is not changing here. And this should also never really be changing. A shouldn't be changing, it's not temperature dependent. So it shouldn't be changing with the temperature or with little k over here, but those could change with temperature. Okay, so the experimental value shows that we could get the E of A by taking negative R, and again, this is the R, the version in joules, the 8.415 version, not the 0.082057 version. Keep that in mind when you're working through these problems. So this is the typical form that's usually used for graphing, and what you'll have is 2 different rate constants because we'll be changing the temperature. When we change the temperature of the system, we will alter some of the parameters of what's going on. So this rate constant can change with temperature. Keep that in mind. But ln A will not change because it's inherently a temperature independent factor. It's related to what kind of collision orientations the system needs and stuff like that. So that can get removed. So when we change the temperature, we're going to change these values, and then use of this will help us determine a value for E of A, because R is always a constant. So this is really the trick here that we're trying to determine. And this equation can be used in the absence of graphing it. And this is the key. You'll see some questions like this in an exam or a bonus or in homeworks. This is the form that you'll want to take down and write down. So they give us these example temperatures, and they want us to find the activation energy using all 5 points. You could make a plot for that. Again, you don't have to do that here. You could also just take each set of points, take 2, then take the next 2, and take the last one with 2, and do it 3 times and come up with an estimated E of A. So you could use that multiple times. You could also just pick any 2 points and calculate it. And you could do all the different combinations and average them. There's different ways. Typically, people just pick 2. And they like to pick 2 that are, typically the furthest apart, so that it's kind of, the E of A is stretched over a longer linear period. But it doesn't typically matter. Using the same equation and known values to calculate this. Okay, so this is now for C. They want us to, given the rate constant at these values obtained in B, when you work out the rate constant at a given from the rate constants at these values here. Okay, so they gave us the rate constants. Using the rate constants in this value, and they can get a new rate constant at a different temperature. So you could solve these for rate constants at different temperatures as well if you know the value of E of A. Again, that's not typically how this is used, but typically B is your most common way that we see this equation being asked on an exam or a question, but be aware that you can also do like what's going on here in C as well. Again, you're not going to have to plot this. This is very tedious, but you should have a basic idea of the theory that goes behind plotting this, just so you can get an idea but again, it's not going to ever be necessary for you to do. Again, we can substitute in these values, and they're just the provided values. We plug them straight into our equation, the version that we said was the most important that we were going to look at, and then we'll simplify this all out and calculate a value of E of A. And typically we write this in kilojoules if it should be in kilojoules, if it's a large enough number in joules. But again, check what the problem is asking for, because oftentimes on a homework question, they will tell you what units they wanted it, and you should put it in those units. Then for B, you plug in the known values again. This is, again, very plug and chug type problems. Just make sure, and depending on your calculator, you may want to calculate this section over here separately, because putting these in a reciprocal form might be more difficult. Some students break these problems up into different stages, but at this point, if you're taking this class, you've had enough experience with your calculator that you should be able to work this out. I do have a calculator video that I've developed to kind of show people how to use like a Google calculator if you're less familiar with calculations. But it's always good to work out how can I put these in with parentheses. Make sure, and I would work through in your calculator these problems. Even if you just have to plug the numbers in, come up with the most effective way, because this is the form of the equation you will see on an exam and that you will see on a homework. You won't be seeing these other forms quite so much. But once you can figure out how to do this, again, we're just plugging in the values. We're not doing anything silly. If we've got to take the antilog, again, we're just going to take e to some power to calculate the parts that we're missing here. And then we'll be able to get that. So in this temperature range, a temperature increase of 10 Kelvin doubles the rate constant. Again, it's going to depend on, this is very reaction dependent, but it's also path dependent. We'll see what that means as we get into catalysis. So we mentioned way back in the first lecture this idea of elementary reactions, the idea of the reaction mechanism, right? So now that we have all this background and these different mathematical ways of approaching rates, now we're going to get into sort of the more interpretive steps, right? So when we're given a chemical equation, this equation is a fundamentally thermodynamic description. So it doesn't tell us how it happens, it just tells us that it happens and how and what that means, a reactant to products. How that happens mechanically and physically is the study of kinetics, but that it happens is the study of thermodynamics. Sometimes these areas overlap, but in many cases they are wholly independent, because you can change how a reaction happens and yet the same outcome still happens. The thought process kind of goes like this. So I have some waterfall, let's say. The water goes over the cliff and it falls into the river below, okay? I can put a water wheel on the waterfall and make the water turn something, so the water's still falling. The reactants are still going to products, but now I'm able to capture the energy from that. That's similar to electrically, if I separate components of a reaction, I can put a wire between them. But it still happens. The thermodynamics don't change. Gravity still pulls the water over the cliff, regardless of how I do it. Maybe I build a water slide on the waterfall, and so now there's a slide. The water still falls to the bottom. That's the thermodynamic question. Does the water fall to the bottom? But how the water falls to the bottom is the kinetic question. The mechanism of a reaction is fundamentally a kinetic question. So it's not something I can determine just from saying that the water falls. How it falls is, I'm ultimately going to have to go look, what actually does take place. So when we study reaction mechanisms, we break them down into what are called elementary steps or elementary reactions that sum up into this overall reaction that predicts what actually happens. So whatever mechanism I propose kinetically has to be consistent with the thermodynamic outcome. The reactants have to go to products. How they do it is what I'm trying to figure out. And I can do that by kind of using this elementary reaction process that we'll delve into. So this is my overall reaction. This is the thing that happens, right? Reactants turn into products. Because I say experimental evidence suggests this reaction takes place by a two-step mechanism. Now, what does it mean by experimental evidence? That's what we're going to study in this section. What evidence would support this mechanism? But typically, to be an elementary process, that's one where the rate of that process, the rate of that step, the rate law, is exactly what it says on the tin. So maybe this overall reaction, maybe something's zeroth or second order in NO2 or CO. That's possible, right? But if we say that a reaction is elementary, then that means that the rate law for this step is NO2 squared. It's second order in NO2. This first step is. That's the rate. It is exactly what it would look like stoichiometrically. That is what it means to say a step is elementary, is that its rate law is that. It is exactly what it looks like. Similarly, this step's rate law as NO3 times CO. And it's second order, but it's first order in each of these two. That's what it means when it says that this is elementary. That's how I know that, is because they told me this. That's not true up here necessarily. It might be true, but it's not necessarily true for a general reaction. Unless I'm told the reaction or the step is elementary, I'm not allowed to make that assumption. Okay, so in the first step, two NO2s collide with enough energy to reorganize into this step. And then in the second step, this collides with this and then performs it, right? So how could I support that maybe this mechanism actually does happen? Well, if I could measure the presence of NO3, that might support this mechanism, because there's no reason to think NO3 exists from the first principles, from the overall reaction. But if this mechanism is true, I might be able to measure NO3. You see it may form here and then go down here. I may not, though. If this second step is so fast that every time this happens, it's immediately consumed, I may not be able to see it. Or if NO3 happens to be really unstable, and so it doesn't exist for very long for some other factor, I may not be able to measure it. But in theory, if I could, that would help support this mechanism, wouldn't it? It might also help support this mechanism depending on what the overall rate law was up here. And that's what we're going to delve into also as well. So they show how this could be broken into steps. Okay. So the chemical equation for an elementary reaction is a description of an individual molecular event that involves the making and breaking of bonds, right? The balanced equation is only the stoichiometry for the overall process, but it does not tell me how. Okay, elementary reaction describes individual molecular event. That's what I mean by, like, their rates have to be what they say they are. And any elementary steps that I propose, no matter how many steps I have to sum up, like they show here, with a kind of Hess's law approach into the overall reaction. I can't have anything extra. That's first rule. That you have to have that. Okay, and like we said here, NO3 is an intermediate. It's something that's not predicted by the overall law, but it shows up in our assumptions. And if that's true, then maybe I can measure it. And elementary reactions are classified also based on what they call their molecularity, which is how many things have to collide. Sometimes they'll call it unimolecular if there's only one thing. It just falls apart, for example, in this example. That's unimolecular. Bimolecular is where two things hit each other. Trimolecular is where, or termomolecular, they hit each other, and then you can keep on going from there. But most systems are either unimolecular, so they have a molecularity of 1, or they have a molecularity of 2. Anything beyond that, you got to have a really good reason, because things like that just don't physically happen. The experimental evidence is that those events just don't occur very often. They're so rare that it's not really conceivable. So here's bimolecular, where you have two things collide. Okay. And termomolecular, these are 3. They're very rare. It's really hard. They compare it to pool, where hitting 3 balls at once is really hard. Some require this, but that will just suggest that this reaction is really slow. If a termomolecular system is necessary, then that reaction is probably really slow or uncommon in some other way. Bringing these together might require the presence of something else. We'll see that in catalysis. So identifying intermediates and molecularity, right? So we show in this first step, this is unimolecular. It's a unimolecular decomposition in the first step, and then this is bimolecular. The chemical equation for the overall, right? These two add up. This O is an intermediate. It goes away. N2O goes to 2N2O goes to 2N2 and 1O2. I can just kind of see that by looking at it up here, but you can see how you'd add up the steps to get this. The intermediate is obviously this oxygen atom, which exists but is not very stable, right? And then what is the molecularity for each of the steps? We saw that. The first one's unimolecular, and then the second one is bimolecular. You can't really talk about the molecularity of an overall reaction. I like that they have D. This is an invalid question. If I was told that the overall reaction was elementary, then I could say that it's bimolecular, but that they would have to tell me to assume that it is elementary. If a reaction is proposed and they tell me it's elementary, then that means that I can assign a molecularity and it occurs in one step exactly as it said, and its rate law is exactly what it appears to be based on the stoichiometry. That is only true if they tell me that. I can't assume that that's true. If a step is elementary, then that is true. The rate for this step is also just this to the first power. we'll see that as we go forward. So rate laws for elementary reactions, right? So if a reaction is stated to be elementary, then this is the case. Then if this is the equation, this is the rate. It is exactly what the stoichiometry tells you it is. Like at the beginning of chapter 2 where we were told that we couldn't make that assumption, if we are told that a reaction is elementary, then that's the information we need to make that assumption. We're being told, do go ahead and make that assumption. If it's a unimolecular reaction, if it's elementary, then it is exactly what it says on the tin. So a unimolecular reaction is always first order in the concentration of the reactant. That's just always true. Same thing is true if it's bimolecular, it is second order and it's first order in the two that are both there. Keeps it simple. And they talk about the frequency of collisions, doubling the concentration doubles the frequency of collisions. This is the basic theory that connects this assumption back to the collision theory that we talked about earlier. If we increase the concentration, then we're also going to increase the number of collisions. This kind of already makes sense from what we've seen earlier in the chapter, though, so not going to take too much of a point on this. But here's an example of the conversion of bromomethane to methanol in a basic solution, because this bromide ion comes off, okay? Not going to really worry about what this reaction means other than that. We just know that they told me this occurs in a singular bimolecular step. Telling me that, using the term bimolecular as a single step, is another way to say that this is an elementary reaction. Again, they can use the word elementary, or they can imply that by saying single and some molecularity in a step. Because an overall reaction that isn't elementary doesn't have a molecularity. So if a reaction has a molecularity, then it's elementary, okay? So then that means this is the rate law. The rate law is exactly what it looks like from the balanced equation. Bimolecular reactions of this type would have a second order reaction. The rate law for this, if this is a bimolecular reaction, is this right here. The overall rate law for an elementary reaction always equals its molecularity. That is also true. So these are just examples. If the reaction is elementary, they have this molecularity and they get this rate law. Keeps it simple. Keeps it simple. Okay, so now that we have all this background kind of set, we can now try to use this to get some sense of what's actually going on, right? If a proposed mechanism is plausible, then the elementary steps have to add up. We kind of implied that a little bit earlier. Also, the mechanism has to be consistent with the experimentally determined rate law for the overall reaction. If a reaction is overall, then that is, I'm saying it's not elementary. It needs a sum of elementary steps to describe it. And that's how we can describe reactions that are not elementary. If a reaction is not elementary, we can get to it with a sequence of elementary steps, and that's a way to describe it in a way that lets the rate law make sense. So we can rationalize why the rate law is not the stoichiometry. Like we saw earlier, we said that we can't assume rate laws are the stoichiometry, and this is the explanation as to why. So if we have a multi-step reaction, and we have some overall reaction, right, and we break it up into two steps, this is a proposed mechanism. And this will be like how they would propose it in a homework question or like on somewhere. They would say that this first step is slow and rate determining, which means that the overall reaction's rate typically is the rate of the first step, because the fast step is so fast it doesn't appear in the experimental data. So this is typically the rationale for why a rate law might not match the apparent steps in an overall reaction, because it's actually based secretly on some elementary step that composes the reaction mechanism that really does happen. So, for example, if this is the slow step, then I might be able to say that the rate of the overall reaction might end up being NO2 squared. That would rationalize this, that's in there, K times NO2 squared. That is actually the rate law. That would be an experiment that could confirm this. That would support that this mechanism is true. The rate of the overall reaction is determined by the rate of its first slower step. Now, sometimes the slower step is not the first one, but typically the slowest step sets the rate law. That's the way that we understand this. In the second step, the unstable intermediate reacts as soon as it's formed. So that might mean I might not be able to see this because as soon as it's formed, it's consumed, because this step is very slow. So it doesn't ever produce that much, and as soon as it is produced, it powers the second reaction. So because the rate law for the overall reaction, depends on the mechanism, it's going to provide some clues as to the mechanism, right? So if this is the experimental rate law, we might not see why that is from the overall reaction initially. It might not make sense why CO isn't relevant to this rate law. I mean, again, the assumption would be that it's elementary, that this collides with this and then forms this. Makes sense, but it doesn't always happen that way. And a rationale could be that there's some slower step. So sometimes when you get a rate that doesn't match with your overall reaction's apparent elementariness, which it's not elementary is what you're finding, why it's not elementary, you can produce another step that's elementary, whose rate law does match up with the observed rate law, and then use a faster step to kind of clean up the process, whether it's first or second. It can depend on whether you observe an intermediate. Sometimes you observe an intermediate and it'll tell you the sequence of the steps. So rate law predicted by the proposed mechanisms follows directly from the molecularity of the step. So you can see how this would make sense with the rate law that we have. Sometimes, like I say, you have an initial fast step. You have some initial fast step that's, in this case, they talk about it being reversible. That's really a thing for chapter 13, but we'll introduce it here. If this first step is fast and can go backward, which just means that it doesn't really accumulate a whole bunch, but it can quickly resupply as it's consumed. If this can feed this reaction, then it can keep producing more. So this is not going to be rate determining. The slow one is rate determining. You don't have to see rate determining. If it says slow, that's the rate determining one. And then this is fast, so overall. So I would predict based on this that my rate law would be N2O2 to the first power times H2 first power. Exactly what's down here. And I didn't even look down here. I could figure that out by just checking what the elementary rate law would be for this slow step. And if that's the case, then this is what I observe. Now, when I look at the overall reaction, the problem is I don't have any N2O2 in the overall reaction. And I wouldn't assume that it existed, because if I just did this reaction, there's no reason for me to think I need N2O2 or that it even exists at all. So I will need to somehow restate this reaction in terms of things I really do have. So I'll have to go back up here and look. That is something to keep in mind. This H2, though, is there, so I don't have to worry about that one. I just got to reconfirm this back into things that are present. So we'll learn how to do that in a little bit, but this is the rate law that we get because it's the one from the rate determining step. But we're going to have to see how to get rid of this intermediate that we don't need. Okay, so the experimental rate law is this. Okay, so, and we write the predicted rate law again. We write that here again. So how could we replace that? How would we have a way to replace this N2O2? We could kind of chase it through the whole reaction, right? We could kind of figure that out, and that's what we're gonna see how to do. So to eliminate the N2O2, we can assume that the fast reversible step is some equilibrium that we'll talk about in 3. So they get this reverse rate. And then we can use that to kind of convert this back and say that since this rate is related to this guy over here, this 2NO, that maybe we can substitute 2NOs for N2O2. And we can. We just have to make sure that our rate constant now is not going to be this K2. It's going to have to somehow also include this K1 over K to the -1, this reverse K. We're going to have to make this be a little ratio by dividing these two rates by each other so we can come up with like a conversion factor, right? So that's what we've done. We've said that these two rates have to be equal because this achieves some equilibrium. Again, this is a bigger assumption than we really need at this point in the course, but you get the idea. So really, typically what we want to do to replace this N2O2 is we want to find another part in the reaction that gives us something equivalent in terms of something we do have in the overall rate law. So this is kind of the most complex example because we have to go back to something up here. But typically, that intermediate will be formed, and we can go backward to the things that form the intermediate and plug those in place of the intermediate's concentration and use that to get the correct rate law. Again, the overall K, all this mess down here with this K2, K1, and this, is then eventually just going to cancel out, and it's just going to be the overall K for the reaction. We're not really going to observe these as 3 different numbers in the real experimental carrying out of the process. But now you can see how I could go back and get NO squared. It's really from the fast reversible step at the beginning. So they say here that this reaction has a second order rate law. Okay, so this doesn't occur as a single step. If it did, it would be third order. And that's the first observation that the book makes, and that's a good first observation. We can tell that this is not a single step because this rate is not the rate that the single step would observe. So then we are proposing a plausible sequence of steps. I'm not going to have a question that asks you. In many cases, there are an infinite number of possible steps that conform. You look for more experimental evidence than that. And that goes back to what we talked about at the beginning. We need something that conforms to the rate law that we observe and that adds up to the overall reaction. Those are the only two requirements. So there'll be homework questions that ask you, is this mechanism possible? Is it plausible? But you won't be asked, for example, to just come up with your own sequence of elementary steps to answer a question. Just keep that in mind. So plausible sequence of elementary steps. So they give us this here. Is this possible? Okay. First of all, does it add up to the overall reaction? Yes, it does. This cancels out. These go down here. These add up, and then this ends up down here. So that works. Then does it match with the rate law? So if I look at the slow step, does it have the same elementary rate law as what it is I'm looking for? Yes, it does. So that is a way to get the rate law that doesn't match up, so we know it doesn't occur in a single step, is by assigning it to some slower rate determining step. This is the simplest way to do it. I like this example because this is commonly what you'll see. Okay, so let's talk briefly about catalysis. This is sort of our last section here. So a catalyst is something that can increase the rate by simply being present. So something you have to realize is that all these models of different reaction rates and processes, they all assume that a reaction can only happen one way. But that's not true. In reality, reactions are typically taking place by a variety of different mechanisms simultaneously. And so what we observe is sort of an overall average of all the different ways the reaction could take place and is taking place. And the mechanisms can change with temperature. They can change with the presence of other things, which is the catalyst. And they can change with other parameters that are going on around them, you know, the presence or absence of light or other ways of getting energy into a system. And so a particular mechanism is not necessarily locked in stone, like it always happens the same way. Even if a reaction always happens, the way it happens may not always be the same every time or under every set of conditions. And a catalyst is just one of those sort of an identification of one of those factors, right? A catalyst is a substance. It's present, and its presence helps the reaction go, but it's not consumed. For example, maybe it's something that things can stick to, and when it sticks to them, it brings them together and helps increase the odds of a successful collision. That's the most common way that a catalyst works, is it's like a surface or it's like some biological component, some kind of protein complex, and it sticks the two into it. The two reactants get stuck in it, and they react, and then they can leave. So it holds them together to overcome steric factor from our Arrhenius equation and to allow reactions to happen at a lower temperature faster. Sometimes, typically we can think of a catalyst as something that lowers the activation barrier. Okay, it lowers the activation barrier, but it can't cheat thermodynamics. It can't turn products into reactants. It can't unboil eggs. Okay, it can only accelerate reactions that are going to happen by providing a faster way for those reactions to happen. It is also possible, as an aside, to produce what's called an anti-catalyst, which blocks a mechanism and makes a reaction slower by raising E of A by blocking a possible way for that to work. Such things also exist. They're just not common, and they're sort of proposed in theory the same way as a catalyst is. It's something present, it's not consumed, so it's not damaged by this process, it's not used up in any way. It just is there, and its presence allows the reaction to happen with a lower barrier to activation. It provides an easier path, like a bypass, around a slower mechanism. So they say this is manganese dioxide. Black powder speeds up the thermal decomposition of potassium chlorate. So its presence means I don't need as much heat to start with. In the absence of it, it decomposes very slowly, even when heated. But a small amount is mixed with before heating, rapid evolution occurs. But we can also recollect this catalyst. It's not used up. It's not a reactant or product, but its presence changes the path. That's the way to think about it. How does it work? It accelerates the rate of reaction by making available a different, lower energy mechanism for the conversion of reactants to products. So it lowers our E of A. That's what it does. Highly unstable with respect. Hydrogen peroxide decomposes very slowly because of the high activation energy. If we provide iodine, this helps it decompose faster by providing a cheaper, quicker way with a lower activation barrier to happen so that the reaction that was already going to happen can now happen faster. And they propose a mechanism that incorporates the catalyst. A catalyst has to be regenerated at the end of all of our processes. Intermediates get canceled out, but a catalyst has to end up back at the end. It'll be present on both sides. You could cancel it out. Its presence does nothing to the overall thermodynamics of the process. That's the distinction between a catalyst and an intermediate. An intermediate gets canceled out. And also, the other thing about a catalyst is a catalyst can appear in the rate law. It's not typically done, but the reason that it can sometimes appear is that its concentration, having more catalyst up to a certain point, can increase the rate by making it more available. But in other instances, the amount of catalyst may or may not matter all that much. It's going to depend on the reaction. Sometimes a very small amount of catalyst is all you need and the reaction just takes off. Sometimes you add more catalyst and you get more speed up to a certain point. Up to a certain point, this will drop out of the rate because at some point there'll be more catalyst than there is stuff to catalyze. So it won't do anything by itself. So a catalyst can appear in the observed rate law, but it will cancel out in the overall reaction, and it will cancel out of all the steps. It'll appear on the right and the left, and it will cancel out. So kind of like an intermediate, it'll be produced and consumed, but unlike an intermediate, it's coming from an exogenous source. It's coming from the outside. It's not produced or consumed by the reaction itself. These are just other things to help you distinguish the two. They say here, a catalyst is consumed in one step and regenerated in a subsequent step, whereas an intermediate is formed in a step and consumed in a subsequent step. Important to realize. Catalyzed pathway may have a faster rate because of a larger frequency factor or smaller activation energy. These two can be difficult to distinguish, but they both can sometimes contribute too. By holding two together, they can increase the frequency of good collisions. They can also lower the activation energy by somehow weakening the bonds. So imagining some metal surface that things stick to. When they stick to it, their electrons are pulled into the metal, and so they're more chemically available, so it lowers the activation energy that way. And because they're held, they increase the frequency of collisions on the correct sides of the molecule, so they're not floating around so much. So they get more collisions too, more successful collisions. So both of those can happen at the same time. So they show this is a reaction process with a catalyzed pathway. First of the two is higher because this first step is rate determining, and that's where the catalyst is really showing up, but sometimes you get two little bumps here. Sometimes when you have a catalyst, it just drops the entire thing. And sometimes you get a little shape out of it too. This is modeling a particular reaction, so there's a little more subtlety going on here. So then there's also two different kinds of catalysts. There's homogeneous catalysts and heterogeneous catalysts. Real key is homogeneous catalysts are in the same phase. Like if everything's a gas, they're a gas too. If it's a homogeneous catalyst, for example, they talk here about how NO is a homogeneous catalyst, nitric oxide. NO is a homogeneous catalyst because it's in the same phase. It's a gas with everything else. Whereas like platinum metal that catalyzes the decomposition of certain organic compounds is a heterogeneous catalyst, some surface that they coat tiny particles in a catalytic converter or something like that. And typically heterogeneous catalysis involves the attachment of something to the surface, an adsorption, a conversion on the surface, and then a desorption of products from the surface. So it's this three-step process, and this is common for any kind of heterogeneous catalyst. Even when it's not a solid surface in a gas, it could be a liquid that sits on a solid surface, or it could be solids floating in a liquid. They interact with the surface or the boundary with this other phase, and then that drives the reaction. They stick to it, and then they're released from that in some way. So there's some holding that typically is involved, or some interaction with this other phase that allows this to happen. So they say here, like, this is platinum catalyzed, or it could be platinum, it could be some other metals too, but platinum is most common. Platinum catalyzed hydrogenation. So this compound attaches and the hydrogens attach to the metal surface, and they migrate along the surface, which keeps the individual hydrogens stable, so they don't have to be H2. They can kind of float along the surface and have the metal help them so they can feel more stable. H by itself, without being an H2 as a gas, is not very stable, but the metal is helping to stabilize them. And then the H finds this other one, and then it helps it react. And this is being held down by the electrons in the double bond in it. Again, we're not going to go into detail about it, but just understand this 3-step process, or 4, the way they show it here. And this may be a bonus question on catalysis on the exam. Then we talk about enzymes. So enzymes are just like this. There's different ways of understanding enzymes, but the most conventional and true enzymes are just catalysts. So that means they don't have any kind of, they're not energized. They don't get any energy put into them. They are just a structure, like a little complex protein machine that things plug into, and then another thing plugs into it. Then the protein machinery helps them interact, and then it releases the products. This is a true catalyst. Just like the metal surface, just like the gas, we can in fact describe them the same way and measure the enzyme's activity with its turnover number and how effective of a catalyst it is. You can actually measure any catalyst with a turnover number. These enzymes behave just like every other catalyst that we understand. They're just made of complex protein structure. Their structure is interesting and more complicated than just a metal surface, but their principle from a thermodynamic standpoint and from a kinetic standpoint is the same. Sometimes they also demonstrate a lot of specificity, like they only will interact with certain reactants. They have a lot of specificity sometimes. Sometimes they don't. Sometimes they're pretty loose about what they accept into them and what kinds of reactions they can catalyze by providing surfaces. But they work basically the same way. Some catalysts, some enzymes involve metal ions that help with the transfer of electrons from reactant to product to help them react with each other. Some of them don't. Some of them are just more holding them in there. But all of them have that same basic principle where they're not powered, so they're not consumed by the process, and they can speed up processes that would otherwise already happen. So they're not changing the position of thermodynamics, they're just lowering an activation barrier and speeding up a process. This is important for life's reactions because sometimes life needs a reaction to happen a lot faster than it would normally happen, and a way around that is to make an enzyme. Enzymes can also prevent bad reactions from happening by speeding up the good ones that compete with the bad ones. These things can also happen. They talk about how an enzyme here digests starch into glucose, but it cannot break down cellulose because it doesn't have the structure to fit that in there. And they talk about how there's an enzyme substrate complex. So this activated complex also is similar to what would happen on any other kind of catalyst surface. So the activated complex is just where the substrate sticks into the enzyme. And some enzymes are very specific. That's where they talk about the lock and key. Not all enzymes are this specific, though. But this just kind of breaks down the enzyme and uses the same kind of rate ideas that we've discussed previously to give them a little more of a mechanism and to understand they're not magical, they're not different. They work by the same things that we can model in other chemical systems. And they give us an example of like an active site where a reaction could occur, where electron exchange or something could happen, and how you could reach a maximum rate where the enzyme is saturated, where you have enough stuff that you keep all the enzymes occupied all the time. And that's the end of chapter 12. Make sure you go back and review, take a look at some of the problems. I picked some particular problems to put into the slides. But if there are some areas where you're still a little confused, go back and do some of the other problems in the text that are around those. If I didn't cover some particular problems, that may also mean that I didn't find them particularly edifying for what's going to be on the test. So anyway, I'll make sure you're reviewing the study guides for the exams, and I will see you all in the next session. Thank you. I think we're good now. So how do I turn this off again? I'm sorry, I keep getting confused. Oh, that one.
Off.
Off. Okay.
I think that's it. Yeah. Oh, sorry.